The law of conservation of energy is an important law in physics. It means that energy can neither be created nor destroyed. It has to exist and go somewhere. Now, there are useful forms of energy, and there are less useful forms of energy. And this comes into the concept of entropy, which we'll talk about when we talk about thermodynamics at the end of this semester. But law of conservation of energy just states that the total energy, right, is constant in any process. It can transfer between processes or systems, but the total remains the same. So in my bank analogy, when I talked about how if you have a transaction fee, every time you move money from checking to savings or savings to checking, the bank takes $1. Now, while that dollar disappears from your bank account, it goes somewhere else. That dollar does not magically disappear. So you can have energy transfer out of a system. Like, for example, pushing a box on the floor, energy is transferring quite a bit. Chemical energy from your muscles is transferring into kinetic energy, pushing across that box across the floor. The frictional force from the box to the floor turns that kinetic energy into thermal energy. Some of that thermal energy heats up the bottom of the box, some of it heats up the floor. So the floor actually gets some of the energy from your muscles. Now, the equation your book gives looks kind of nasty, but it's actually pretty simple. It just states that the initial energy of motion, the initial kinetic energy, plus the initial potential energy, gravitational, spring, plus the work done by non-conservative forces, plus other energy initial. So the total energy of the system initially, plus this transaction fee, must be equal to, or minus the transaction fee, because that'll be a negative number, is equal to the final kinetic energy, the final potential energy, and the final other energy. Well, what do I mean by other energy? Well, there are actually many, many different types of energy. Kinetic and potential are mechanical energies, but not all energy is mechanical. Some is electrical. You can store energy through, an electrical system. That's what powers your house. You can actually, a camera flash, for example, is stored energy in an electrical system. Energy is stored in what's called a capacitor that discharges very quickly. Or the paddles you see on those ER shows, right? Clear, boom, and they shock the patient. Before they shock the patient, the energy that they build up is stored in the electrical system in that device, in that defibrillator. Thermal energy, heat. You can actually power things from heat. It's not a very useful form of energy, but you can do it. Nuclear energy, right? The energy stored in the bonds in the nucleus of atoms, which can be released rather explosively, as we found out, in Hiroshima and Nagasaki. Chemical energy, energy between the bonds of atoms, which powers us. That's how we store power. Not quite as powerful per unit mass as nuclear, but you can still have quite a bit of power, right? C4 explosives, dynamite, those are all chemical bombs where energy is released very quickly. Radiant energy, if you've ever gotten sunburned on the beach, you know that the sun's rays hold energy, and so on. So those all represent other energies. Now in physics, we're somewhat interested in this, of course, because physics deals with electrical systems. We'll deal with that next semester. Nuclear systems we'll deal with next semester. Chemistry is all about chemical bonds and the energy of chemical bonds, why some chemical reactions occur and why others don't, why some chemical reactions are exothermic, why some are endothermic, all deals with the conservation of energy. So physicists are interested in this, but right now we're going to focus in on the mechanical energy aspect of this. So talking more about kinetic energy, potential energy, and so on. But this law of conservation of energy, one last thing I want to mention about it, it isn't derived anywhere. It's been found experimentally. It's just that every experiment we've ever done, energy has always been conserved. Always. We have never been able to do an experiment where it has not been conserved. In the few times where experiments have shown that it doesn't appear to be conserved, that paradoxical result has actually resulted in new science. There is a gentleman, Enrico Fermi, who, when doing a nuclear experiment, added up the energy before the system and the energy after the system, and they didn't quite match. There was missing energy. So either he found a break in the law of conservation of energy, or there was something else going on that he couldn't see. And the law of conservation of energy is such a powerful law that he actually predicted the existence of a nearly massless particle which is weakly interacting with matter. So that's why it was tough to detect. It was neutral, it didn't have a charge associated with it, very, very low mass, and took away a small amount of the energy. He postulated this little neutral particle, he gave the name neutrino, which means little neutral one. We now know that neutrinos exist. He speculated their existence because of an error he saw in the law of conservation of energy, suggesting there was missing energy. He said that could only exist if this particle took some energy away. They searched for the particle and they found it. Neutrinos are actually amazing little tiny particles. In the area the size of your thumbnail, 1 trillion neutrinos go through every second. But neutrinos are so weakly interacting, you'll actually get hit by one of them in your lifetime, on average. Most of them, the vast, vast, vast majority of them pass right through you like you're not even there. So the law of conservation of energy is very important in physics, and is a lot of our understanding of how things behave is due to this law. One concept dealing with work and energy is the concept of efficiency. Efficiency is just, given an amount of energy, how can you convert it into useful work? Chemical energy in our muscles. Can we convert 100% of that into work, or is some lost? And some is lost, right? Your body temperature, 98.6, you generate heat. That heat is a waste product in the chemical processes in your body. Now, some of that waste product heat is needed to keep your body temperature at 98.6, right? Too cold or too hot, the chemical processes in your body don't work quite the same and you will die. But, this excess heat, we wear clothing in order to maintain our body temperature at around 98.6. So the efficiency here is just the useful energy, useful work output, my apologies. Useful work output over the total energy input. Now, for those of you buying a house at some point in the future, and I just happen to actually be in that process right now, one thing you can look at, or if you live in a house, one thing you can look at is go down into your basement or wherever you're keeping your furnace and look at the energy efficiency rating. Most furnaces nowadays are 92, 93, 94% efficient, which means that the chemical energy that comes in from the natural gas or oil or coal or whatever you're burning, I doubt any of you have nuclear powered furnaces, around 95%, or the efficiency of 0.95, about 95% of energy efficient. That's wonderful. That's what you want. You're paying to have that natural gas delivered. You want to use as much of the energy in that natural gas as possible. Now, that's because the chemical energy is being converted into thermal energy, heat. That process is incredibly efficient. It's much harder to convert chemical energy into kinetic energy, energy of motion. A car engine does that, right? Burns gasoline as the energy input, as the chemical energy in the gasoline, and the output, the work that you want, is for your car to move forward. Most engines are actually not very energy efficient. There are ideal engines called Carnot engines, and we'll talk about that when we talk about thermodynamics, but even those are 30% efficient or less. So, for a car engine, you might only be getting 20% efficiency or 25% efficiency at best, which is actually not bad for an automobile, because there is a limit, again, as to what the ideal efficiency can be. You will never get an automobile at 100% efficiency. That's not possible. Efficiency can never be more than 100%. We'll learn that when we talk about thermodynamics as well. You cannot get more work out than the energy you put in. right? You don't add a gallon of gas and then suddenly fly back and forth to the sun a few times. That's not going to happen. So efficiencies, in your book lists a bunch of efficiencies as to efficiencies for activities that you can do. Walking or climbing, how efficient is your body at converting chemical energy into mechanical energy? Furnaces, power plants, that sort of thing. Converting kinetic energy into electrical energy, a power plant, right? A waterfall or a wind turbine converts mechanical energy, the kinetic energy of the wind and the water into a turbine and produces electrical energy. How efficient is that process? So you can calculate that using this relationship. Now note, this efficiency, when you divide it, has to be between 0 and 1, right? 0 just means you get no work out for the energy you put in. Your efficiency can't be less than 0. That means that you put no energy in and suddenly the machine starts not doing work. I mean, the negatives don't work. These always have to be positive. And it can't be more than 100% efficient, or this equation cannot be more than 1. And I have it equals, less than or equals to here. Really, it's according to the laws of thermodynamics, it's really less than. You can't have something 100% efficient, or very, unless it's theoretical. So if you want the efficiency in percentages, just multiply the output of this by 100%. So the efficiency will be between 0 and 1. Multiply that number by 100% to get the efficiency in percentages.